The principle of X-ray fluorescence analysis can be explained by this simplified model with iron as an example. 26 electrons surround the atomic nucleus and are uniformly distributed over a total of 4 shells in space, which are referred to as the K, L, M and N shells. When excited by high-energy X radiation, an electron is removed from an inner shell. The vacancy generated in this way is now filled by an electron from a higher shell. The energy released in this step is emitted as a light quantum. This quantum of light reaches the detector, in which its energy is determined. When this process is repeated many times, plotting the number of photons detected against the energy of these photons results in the measured spectrum. As the energies of the emission lines depend on the atomic number, Z, and are also specific to the element under study, different elements can be identified and quantified by their characteristic fluorescence radiation. For X-ray fluorescence measurements in ANKA, the synchrotron radiation is modified in various components on its way to the sample. Absorbers are used to modify the spectrum of the excitation radiation. The desired wavelength range is selected by a monochromator. Diaphragm systems are used to mask undesired edge zones of the primary synchrotron beam. The range of measurement is explored on the image of the light microscope installed in the measuring station. The X-ray is focused by a capillary to a small spot only a few micrometers in size, and the characteristic fluorescent radiation is captured by the X-ray detector and evaluated in the multi-channel analyzer. The sample is scanned and the fluorescence data are obtained point by point in this step. The measured data produce a two-dimensional representation of the trace elements studied in the sample. Synchrotron X-ray fluorescence analysis, or SciXRFA for short, allows trace elements to be detected in a variety of materials, such as metals and alloys. As a result of the special design in a vacuum chamber, all elements, from light sodium to heavy uranium, can be detected in ANKA. As a function of the analytical problem at hand, two possibilities for excitation exist in ANKA. The use of polychromatic radiation allows the simultaneous examination of a large number of elements. Single elements in very low concentrations can be determined by specific excitation by monochromatized light. SciXRFA is a non-destructive method. In this way, valuable objects of art can be examined for their authenticity, and historical classification is possible on the basis of their fingerprints. The X-ray beam, focused to a few micrometers, allows multi-element analyses to be conducted with high local resolution on very small samples, such as single cells, microorganisms, or even smoke particles. Extremely small amounts of substances, such as 1/4,000,000th of a gram, 1 femtogram, can be detected in this way. Extremely high sensitivities of detection are required also in semiconductor production. For selective examination of semiconductor surfaces for minute traces of impurities, the fluorescence measurement station in ANKA can be made to let the X radiation impinge on the sample under a very flat angle of incidence. Changing the angle of incidence also allows analyses to be conducted with depth resolution. In this way, a wide variety of samples can be characterized.